Let's go and review some things we've talked about in our last couple of lessons. We've begun talking about devices intended to make work easier. We talked a lot about work, we talked about power, and what are devices intended to make work easier, class? Machines. And we talked about 6 simple machines. Simple in that they don't have a lot of complicated parts to them, and simple also in the sense that they can be used in more complex machines, put together in various ways. What are those 6 simple machines, Michael?
Lever, incline plane, pulley, wheel and axle, wedge, and screw. Sorry,
he won. All right, you got all 6 out of 6. Of course, he had an extra day, right? So 5 out of 6 the day before. It's a tie, right? And the first machine we talked about, Audrey, was the... And we basically said a lever is a really long object that should be... But it has to pivot, right? But it should be inflexible. That's going to be key. A long, inflexible object that pivots. And it can be used to pry in some cases. It can be used to push in other cases. Used for all kinds of different things. I think it was Archimedes said, if you give me a lever long enough, I could literally move the planet. Now, he could use the moon as a fulcrum. And it's true. I mean, if a long enough lever, I mean, you can literally move any load if you have a long enough, strong enough lever. So it's very powerful, though again, how would he get out there to use that? Anyway. But theoretically, he was correct. The point he was making was there's infinite potential there if you can come up with something long enough, strong enough, not that wouldn't bend. With the lever, we said it has to pivot. What do we call that point at which it pivots? The fulcrum. The fulcrum. What do we call the object that the lever is intended to move? In Archimedes' case, the world. The load. Good. And so we put in force, call it input force or the effort. We put in force on one side, and as we push on one side, the other side lifts up. Or as we push in one place, another part of the lever will lift or will move. And so we said there's a few different types of levers, a few different classifications of levers. We said one class of lever, the one that I'm picturing with Archimedes, using the moon as a fulcrum and pushing on one end and the other end lifting up on the world, would be where the fulcrum's in the middle. We call that class A. Class 1 lever. Class 1 lever, what was the example I gave you? A seesaw, where the pivot's in the middle and the 2 people are on opposite sides. The input, output are on opposite sides. That's usually what we think of when we think of a lever. And we said that a class 1 lever, if you push on the long side, you will greatly increase your, what's the mathy word, the physicsy word for it? Force. You'll increase your force. But if you push on the short side, you'll increase speed on the other end. We said a class 1 lever can do either one. I said for a class 2 lever, what was the example I told you to remember? Wheelbarrow, which if you picture the wheelbarrow, where is it pivoting, class? At the wheel, at one end, right? Not pivoting in the middle, but pivoting at an end. What's in the middle of a class 2 lever then? The load, right? The load of the wheelbarrow, and then you lift on the other end. So if you can picture wheelbarrow, you can remember the order. Fulcrum at the end, output in the middle, that's the key, and then input at the other end. We said that a class 2 lever can only multiply force, because the output lever arm will always be the short one because it's in between. And then we said the class 3 lever, what was the example I gave you? I actually mentioned a few, but...
baseball bat.
Baseball bat's the one I gave you. Where does the baseball bat pivot when you swing?
Wrist.
At the wrist. Where is the force going in?
The bottom.
The hands. So the wrists are here, the hands are here. Now the input is really close to the pivot, but the input is the next thing. And then at the end of the bat where it contacts the ball, that's the output or the load, right? So as you swing, what's in the middle? The input force. Now it's not in the center middle, but it's in between where the output and the fulcrum is at. And we said that a class 3 lever will only multiply speed, right? The key is to get bat speed to hit the ball farther. So class 1, what's in the middle for class 1? Fulcrum. Class 2, output or load. In class 3, the input or the effort. We had some equations for the lever. One of them was actually 3 different ratios, all set equal to each other. What was that 3 ratio proportion? Audrey?
So,
we ignored the middle and cross-multiplied, we'd get another equation, Michael.
I'm drawing a blank.
Product of the means equals product of the extremes. Audrey?
F sub I, R sub I.
That's the product of the means.
F sub I, R sub I.
There we go, the product of the extremes. Again, we just ignore the middle proportion. This equation, we actually has a name for it. Do you remember that, Michael?
Law of levers.
Good, the law of levers coming back to you. The law of levers. Because typically this is what we would think of. We very rarely with a lever would picture how far we're moving anything. Right? Archimedes isn't concerned about with moving the world very far. He just wanted to be able to say he did it. Obviously he didn't, but theoretically. Right? Just going to move it a little bit. So we don't care about the distances moved so much as we do the length of the... What are these R's for, class?
Radius.
We can think radius, but as a name, from the fulcrum to where the force goes in, and from the fulcrum to where the force goes out. There's two sides to the lever, or parts of the lever we call the...
Lever arms.
Lever arms. Good, the lever arms. Now again, we're picturing an arm here and an arm here. Well, that's class 1. Class 2, where there's a load down and input force out, there's one lever arm, there's the other, where they actually overlap each other. Right? And then for the input, there's the fulcrum, there's the force in, there's the force out. Well, there's the input, there's the output. So class 1, the two arms are separate, which is where they get the name. But class 2 and class 3 is actually overlap. So the arm isn't a good analogy, but it's still the name that was given. Who are we to argue? All right, so the lever arms and the forces products give us the law of levers. Now, if I just took this ratio, output force to input force, I'd be able to see how much more force comes out than force has to go in. Well, that means the machine is giving me more force. It's multiplying force. In general, what do we call the ability of a machine to multiply force, class? Mechanical advantage. What is it?
Mechanical advantage.
And this ratio of the output force to the input force truly, actually shows me how much my force was multiplied. So this ratio, class, we call the AMA, which stands for actual mechanical advantage. Now, based on distances that are moved, that can show me, or distances that would be moved, or even radii, this one specifically, but this one too technically, gives me what should happen if there were absolutely no flexion, which we kind of assume anyway, absolutely no friction. The IMA, which stands for ideal mechanical advantage. And what units do we use for AMA and IMA, class? None. They're unitless. Force, of course, will be continue to measure in newtons or pounds. Lever arms will continue to be measured in meters, or possibly even centimeters, possibly feet, possibly inches. As long as they match, that's the main thing, allow the units to cancel. And so we can work with this with whatever units we would normally have. But the actual mechanical and ideal mechanical advantage, those are unitless. We were finished talking about the lever that we're going to revisit in a moment, but first I want to review the other simple machine we looked at yesterday, the inclined plane, or in plain English class, ramp, right? And for an inclined plane, we said the purpose of the inclined plane is to do what for you, class? Lift. It lifts for you, and all you do is push. You push, it lifts. So we said that for the inclined plane, there's going to be a certain amount of force that is applied. That's the force you put in. But we said that the inclined plane does what again? Lifts. It lifts the object's weight. So the output force of the inclined plane is the weight. So we said for an inclined plane, if AMA, class, is output force over input force, for a ramp we could say the AMA is the weight over the applied force. Now, this is review from what we've done earlier. To what will the applied force generally be equal if acceleration equals 0? What will counter the applied force? Friction certainly will counter it if there is friction, and generally there will be.
Normal. Well, no.
The weight in the x, right? There's a weight downward, and there's or inward rather, I should say, and there's a weight along the surface. Of course, we usually draw it down here to make it a little easier to make the triangle, but this weight component that's going sliding down the ramp, the weight in the x, those two components will equal, if there's no acceleration, the applied force. Obviously, if there's no friction, then it's just the weight of the x that's being countered. And we did some problems with that yesterday as well. Let's come back, though, to the seesaw problem. Jot some numbers down, if you would, there in your notes, or just on a random sheet of paper. It doesn't necessarily have to go in the notes. Let's suppose we have two little kiddos on a seesaw. Let's suppose my son Timmy and my son Andrew are playing on the seesaw, and let's age them both about another year or two. Timmy at this point is 50 pounds. Andy is 35 pounds. Timmy is 50 pounds, and Andy is 35 pounds. Now, the 35-pounder, Andrew, we're going to sit him at his end of the seesaw. It's a 10-foot long seesaw. 10-foot long seesaw. I think I'm going to jot that down. And Andrew is sitting at his end. But if we put Timothy at the other end, what happens to the seesaw? Andy's up here going nowhere, wondering what's up. He is. And Timmy's down here wondering now what. Okay, they can't balance. They're not the same weight. So I tell Timothy, slide forward a little bit. The question is, how far forward does Timmy have to slide so that they'd be in balance? That's your question. How far forward does Timothy have to slide to balance with his younger brother, Andrew? Take just a moment or two. There's the equations for the inclined plane. Back to the lever. I could move it for you, Kendall, but if I did, then you wouldn't get to see the pretty sparkly stuff. And what fun is that, really? All right, for the problem, we have to consider one of the boys to be the load, and we have to consider the other boy to be the input. Doesn't really matter which one's which, honestly, truly. Michael, who did you put on the input side, Andrew or Timothy?
Timothy.
Put Timothy here, and we put Andrew here. All right, now we know Timothy's force. As Timothy sits on the seesaw, wherever he sits, he's got a force bearing down of 50 pounds. But we don't know where he's got to sit, do we? So we're going to leave his lever arm unknown. Andy, on the other hand, has a lighter force. 35 pounds. And if it's a 10-foot long seesaw, and he's at the end of it, where the seat generally is, his lever arm is 5 feet. Right, 5 feet on each side, assuming it's a normal seesaw. It'd be a strange seesaw that's not like that. All right, so all we do, we multiply, we divide this 50 away, and we get what for the lever arm for Timothy? 3.5 feet. But my question was not, what is Timothy's lever arm? My question was, how far forward does Timothy have to scooch in order to balance with his brother? So his lever arm needs to be 3.5 feet, and the seat would be at 5 feet distance. How far forward does he have to scooch? 1.5 feet. Did we get 1.5 feet forward for our answer? Did we get 3.5 feet for his lever arm at least? Okay, just didn't kind of finish the scooch part. All right, questions on that? Kendall, I don't think you were here the first. Was she here the first day we had the scooch conversation? I don't know. Sorry, Kendall. You're like, why does he keep saying scooch? That's such a weird word. Blame Michael. All right, questions on this? Questions on this? All right. Turn over now to page 171, problem number 10. Page 171 in your books, problem number 10. Let's look at another ramp problem, inclined plane problem. And readeth numero diez for us. What's your Spanish name? Audrey. Audrey? Audrey? See, how do you say read?
Leo.
Leo. I know book is Libro, or Libro?
I think it's Leo for read.
Leo? Audrey, Leo numero 10.
Loaded crate weighing 1,250 newtons is pushed up a plank onto a platform. If the plane is inclined at 10 degrees to the horizontal and the constant is 0.420, calculate A, the item A, B, the amount of force required to push the crate upward, C, the AMA, and D, the efficiency.
First things first, if we know the weight and we know the angle and we know the coefficient, you can set up the entire free body diagram. So, at your seats, solve the entire free body diagram. And then we'll answer all these questions. Michael's nodding. He got the free body diagram solved. Okay, Michael, go ahead to the questions it asks and see if you can figure out the answers to those. I just realized I stopped short in my review earlier. Oops. Yeah, Kendall, you're right. I forgot to talk about the IMA for the ramp. Got distracted. Sorry. She's been like, Mr. Adamski, IMA, but I can't hear what you scream at your computer. I'm sorry. Have your dad text me in the middle of class. Boom, 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 boom. What about the IMA? Ah. Yeah, it's not a live video. That doesn't work. And Audrey, how are you coming on free body diagram? Did you get stuck, or are you doing okay, just kind of a little bit behind?
I messed up a couple steps.
Okay. So the first thing I found was right here. I found the weight and the y. You could start with the weight and the x, it's up to you, but we got to take the weight and break it into the two components. Did you do that?
Yeah.
So are the two components correct? Okay. Did you state that the normal force would equal the weight and the y?
Yeah.
Okay. Did you then multiply this by the 0.42 coefficient of friction? That was the problem. Okay. So yeah, we just need to take that normal force, the 1231.0, blah, 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 multiply by the 0.42, and that'll get us our friction force. And then how do I come up with the applied force right here? Michael?
I did 1 over the sine of 10 degrees.
No, sorry, I'm not asking for the answers yet.
Oh.
How did I come up with the applied force? Once all the other stuff is done over here, how do I get that?
You add the friction and the weight and the x together.
Good, remember the weight and the x and the friction combine to match the applied force. That's the minimum force needed to move it up. So that's what it asks, how much force is required, how much minimum force. It's not accelerating anything. We just add them and that's where we get the 734. So are we good to go now? All right. And again, just kind of a refresher on how to solve this. Now, the questions it asks, it does actually ask for letter B, how much force is required to push the crate upward. So I have my answer for letter B. I'll round off to 3 sig figs class.
734.
Good. The applied force, the force required to push it upward, is 734 newtons. So we actually already solved part B. Now it's interesting, Michael, they ask part A for you to find the IMA first. Almost as if they expect you to be able to get the IMA before you even do the free body diagram. And I realized we hadn't reviewed the IMA yet. Remember, IMA, rewinding our brains here just a little bit, for the lever, and in fact for all simple machines, is the ratio of input distance to output distance. For a ramp, if you're sliding the crate up the ramp, or sliding anything up a ramp, what is the input distance of the ramp class? What distance do you put in as you slide something up a ramp?
The whole length.
The whole length of the ramp, correct? So the IMA is going to be the length, that's your input distance, over, now what's the output distance? What is the ramp doing? It's lifting it. So however high it lifts. So we said the IMA is length over change in height. Class, how do we find IMA for a ramp? Length over change in height. But I don't know the length of this ramp. They never tell me. They also never tell me how high the ramp is going to go. But they do give me something. In a ramp, the change in height would be here, and the length would be here. And there would be an angle formed because there is a change in height at all, correct? The greater the change in height, the greater the angle. So the angle is tied to the change in height, but it's also tied to the length. Because if you have a really abrupt change in height versus a gradual change in height, the length is affected. What trig function relates these two variables to this angle? The sine. We know that sine, class, is
Opposite over
in this case, sine would be change in height over length. Well, that's not the IMA. The IMA is length over change in height. So the sine and the IMA are in fact reciprocals of each other. So we said we can also find the IMA if you know the angle, which we do, by taking the reciprocal of the sine of theta, or the cosecant of theta, but we don't have that button on our calculator anyway, so take the sine and then hit the reciprocal button. So the IMA you could find without doing any of the free body diagram here. Just take the sine of 10 and hit the reciprocal. And what's the IMA of the ramp?
About 5.76.
5.758, blah, 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 rounded 5.76. Notice no unit. I do want to go ahead and put this in the memory. I'm going to overwrite memory 1 here for something we're going to look at here in just a moment. So the IMA of the ramp, 5.76. What this means is, in a perfect world, a frictionless world, which it wasn't, I'd be able to multiply my force by 5.76. Meaning if I push 100 pounds of force, it'll lift 576 pounds for me. Now, thoughts on the frictionless ramp, practically speaking? Is that a good thing? If the ramp is frictionless, I can't push it anyway because I'm slipping, right? And it's slipping and sliding as well. But remember the example from yesterday, frictionless rollers. If you have it on a cart that's got really good wheels, nice smooth wheels, maybe roller bearings in the wheels and everything, well then you're going to be able to negate the friction, and so you can still get traction and just roll the thing up the ramp. Okay, so IMA 5.76, we found the applied force. Then it asks for letter C, the AMA. We said AMA, class, is always a ratio of output force to input force. Okay, class. IMA is always a ratio of input distance to output distance. AMA is a ratio of
Output force to input.
there we go. For the ramp, Because input distance is length and output distance is change in height, we can say IMA is length over change in height. We didn't change the formula, we just defined it more plainly. AMA for a ramp is still output over input, but we said for the ramp class, the output force is the, and the input is the applied force. Well, I have the weight given to me, and I know the applied force is in my third memory. So weight over applied force, let's find the actual mechanical advantage. It lifted 1,250 newtons. I only applied 734.08. What's the actual mechanical advantage?
I have
1.702 blah, 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 or rounded 1.70. Meaning, because of the friction that is here, inherent in the machine and this usage of it, it only multiplies my force by 1.7 times instead of the full 5.76. Friction, again, is what took what was ideal and made it more reality. Kind of like, well, anyway, we've been over that before. All right, there's another question it asks, letter D. It asks for the efficiency. We're going to get to this in another lesson. You'll read about it tonight in your homework. Efficiency, represented by the Greek letter eta, takes this. What you really get out compared to what you'd expect to get out. That's an efficient machine. You ever heard the phrase a well-oiled machine? It comes from automobile parts, where we want the automobile gears and everything, and the engine and all that, drivetrain, to be lubricated and to work well, right? A well-oiled machine runs with a minimum of friction, a minimum of loss of power, a minimum of loss of work. Efficiency, one way we can find it, we'll get to this tomorrow, but just so we can finish the problem, is to take the ratio of the AMA, what we really get, compared to what we thought we would get. So while you've got the 1.702 blah, blah, blah on your calculator, go and divide it by the IMA that we put in the memory. And how efficient is this machine? Well, what you'll get is 0.2956 blah, 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 correct? But we want this to be expressed as a percent. Efficiency is a percent efficiency. So we move the decimal 2 places, we get 29.6% efficient. Yeah, whatever. Not a great number, right? Below 50%. Friction is what takes away that perfect world scenario. All right, but we'll get to efficiency more later. You don't have to put that in your notes yet, just kind of a foreshadowing of what's coming, but I did want to finish the problem. Questions on lever, questions on ramp. All right, let's move on. Next simple machine for you to put in your notes. Next simple machine for you is the wedge. The wedge. W-E-D-G-E. The last E is silent, and that's important. The wedge. Thank you, Michael. I was like, okay, that was a joke, folks. Got a minor chuckle from Michael there. Thank you. All right. The wedge, here's your definition. 2 inclined planes back to back. 2 inclined planes back to back. That describes the shape or the structure. I also like to give you the purpose of each machine. So it's 2 inclined planes back to back designed to cut or split. 2 inclined planes back to back designed to cut or split. 2 inclined planes back to back designed to cut or split. Essentially then what we're looking at with a wedge is an inclined plane and then back to back with it another inclined plane. Basically then this object comes to a point, and imagine as you push the point into something, as you push the point in, the object must be pushed apart by the inclined plane. So we take by the 2 inclined planes, so what was 1 gets pushed apart and gets either cut or split. A good example of this would be an axe blade, right? You've seen, anyone ever actually chopped wood with an axe? Okay, so as opposed to, you've seen it on TV, right? They put the thing there, they get the axe, or it might even be a wood splitter, which is but anyway, whop, and it splits apart, and we got 2 pieces of firewood now. And if it's too big, they take that, they put it back on the chopping block, whop, and it splits apart, and usually they do it with their shirt off so you can see the rippling muscles while they're doing it, and all of that nonsense, right? Okay, so we get the idea, but a knife does the same thing. For instance, if you take a block of cheese, and you push the knife down, what you're doing is you're splitting it apart. Now we think of it as cutting it. Usually we think of cutting as having a sawing motion to the knife, but you can cut just by pushing straight down if it's something soft like cheese. If you think of Thanksgiving turkey, right? When it's all said and done, you've got this massive carcass with much of the meat eaten off of it. But oftentimes what parents will do, I don't know if your moms do this by any chance, is to make some turkey broth. And they take the bones and they soak them in boiling water for a while, add some vegetables and stuff, and it makes all the oil comes out of the bones, makes a really rich broth, which is very nutritious. There's all kinds of studies about the benefits of bone broth, but that's not what this class is about. But sometimes cutting the carcass up can be really hard. If you take a little knife and you start sawing, you're going to be there all day trying to cut through the bones. But probably your moms have a knife block with lots of different knives in it, am I right? And they sit on the counter, or maybe they sit under the counter, and you pull out and there's this one knife that's like massive. It's about this long and about that thick, right? And if you get that thing, you can crunch right through those bones with relative ease. Why? Well, I'm not going to get into the AMA with this thing because there's so much friction involved, it's ridiculous to even try to do any calculations. But we can look at the IMA at least, the ideal, and realize that it's never going to live up to this much height. But when you push down on the knife, or when you hit forward with this axe blade, there's a certain distance that the blade puts in. And the input distance is literally the depth of the blade, or the length of that blade from the sharpest point to the back end of it, right? The output distance is this total width that gets split. Now remember, IMA is always a ratio class of?
Distance of input.
Good, D sub I over D sub O, input distance over output distance. If you get a thicker or deeper blade that is thinner, imagine if you could shrink the D sub O and you increase the D sub I, what you get is something that has a great amount of multiplication of force, theoretically. Again, it's not going to actually multiply this much. This is ideal, but still, the deeper the blade, as you apply a force, it multiplies that force, which is why I think back to medieval times and swordsmen, right? A skinny little blade, like a foil they use in fencing. Yeah, that's not, but you get that big, huge sword with the blade that's like that thick, and of course it tapers to a point, but that thick blade, but narrow. Widthwise this way from sharp edge to sharp edge if it's a two-edged one, right? It's width wide, but it doesn't get very thick. That is a great deal of power. So while chopping off somebody's head could be somewhat of a challenge, use a guillotine blade or that blade. In war, it works really well. You want a greater D sub I, lesser D sub O to increase your force with using a wedge. All right, so deeper, thinner blades work the best. We're not going to actually do any math with that, though, just because the math is complicated because there's so much friction involved anytime you cut or split anything. Let's move on to our next simple machine then. Now that we have a rudimentary knowledge of the wedge, let's talk about the screw. The screw. Now, not thinking of the screw as in the fastener screw. Okay, y'all know what we're talking about with a regular screw. You can picture it for some purposes, but that's basically you want these two things to hold together, so you use a screw and it holds them together, right? What I'm thinking of is like a screw jack. You ever had to change a tire on the car? Not yet. You have. All right. Hopefully in the back of your car is a jack. And if it is, it's not a hydraulic jack, because those are big and bulky and they take up space, and most people don't have those. You will occasionally see on the back of like the Jeep or whatever, the cool looking Jeep, they have this big old jack on the back. Okay, that's not a screw jack. Little bitty screw jack, you know what I'm talking about. It's kind of a zigzaggy thing with a long screw, and there's another screw that goes this way. And as you turn the handle over and over and over again, little by little, it goes like this, and it lifts your car just barely off the ground, but that's all you need to get the tire changed. You want level ground, and you want to stabilize your wheels so it doesn't suddenly, as soon as it lifts up, it starts to roll on you. All right, so anyway, I've used the screw jack before. It's a real pain. But basically, as you turn the handle of the screw begins to go up. A basic screw jack you might see, for instance, on page 167. You see a good example there, page 167, of what maybe this isn't the kind that would be in the back of your car either, but maybe something that will help you to picture this a little bit more. You've got the handle of the screw jack. It's labeled with the letter R for a radius because, in fact, as you turn it, you're making a circle, aren't you? And you turn it round and round and round and round, and as you turn it, the screw will either go up or down, or the jack will go either up or down. Does that make sense? Now, go ahead and picture a regular screw, like with the screwdriver, the fastener screw. there's ridges between the little, on the screw, right? And you've got this little ridge, but it's not perfectly horizontal ridges, are they? It's one continuous ridge that wraps upward. Now, if you've ever looked at maybe a collection of screws, you'll notice that the ridges are all different. All different kinds of screws have all different types of ridges. Some of them, the ridges are more spread out. Some of them, the ridges are closer together. Some of them, really, really tiny screws. There's all different kinds of screws out there depending on what you need. Here's how we're going to define the screw first of all. A screw is defined as machine is defined as an inclined plane wrapped around a rod. An inclined plane wrapped around a rod. And this even defines to an extent the fastener, though the rod is tapered at the end to make a point. But we've got on a screw, we've got this cylindrical shape, if you will, and the inclined plane wraps around it at a perfect continuous angle. It's got to be all one thing that continues to wrap. That's key. Which means that the spacing has to be consistent throughout, right? I have one column, porch post column on my house that holds up, that's supported on by walls on the other side, porch post, and I wrap it with garland every Christmas. And my goal is to get even spacing, okay? More or less successful and slightly OCD about it. But anyway, these have to be exactly perfect. And of course, it's machined that way. This distance between what I'll call the ridges of the screw is called the pitch of the screw. The pitch of the screw is the distance between the ridges. Again, it's technically all one ridge, but as you look at one side of the screw, it looks like a plethora of ridges. Again, some screws have a wide pitch, some screws have a smaller pitch. And you see that in the diagram as well with the screw jack, how there's that ridge on the screw jack. The ridges are much thicker and more pronounced on the screw jack in your car or SUV. But the bottom line is, as you turn the screwdriver handle one complete turn, the screw will turn one complete pitch. Either if you're backing the screw out or turning the screw in, the screw will either go down into or come back out of one pitch. One turn, one pitch up or down. For the screw jack, turn the handle one complete turn, one complete pitch of lift. Now think about this. The IMA. We said IMA is always a ratio of what to what? Input distance over output distance. Well, if you're using the screw jack, and again, there's a little bit of a gear ratio type thing because it's a horizontal turn anyway. But for this type of screw jack, it's really straightforward. You turn the handle one time, that's one complete circle that you're making, right? Your hand, as you turn it, is making a circle. Even the sideways screw jack that we would use on our car, you're turning one complete turn. Well, wherever you grab the handle, right, that's your radius of your circle. And the one complete turn is the distance around the circle. What do we call distance around a circle? Circumference. How do we find circumference? 2 pi r. So the input distance for a screw, or screw jack more specifically, is 2 pi r. That's the input distance. Well, what about the output distance? One pitch. You turn the handle once, it rises one pitch. So there's our equation for the IMA of a screw. It's still input over output distance, but we can define it as a 2 pi r, where r is the length of the handle. I'm not going to use L for length necessarily because the handle is literally the radius of your circle. I think the r is self-explanatory and helps us to remember this. And of course, P is the pitch of the screw. Well, think about it. How could you increase your IMA? Get a longer handle, not unlike a longer lever or a longer ramp. You get the idea? Longer gives you more multiplication of force, but you could also shrink the pitch. A smaller pitch will increase the mechanical advantage as well. Now, again, the frustrating thing is, and you know this, turn, 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 nothing's happening, turn. Well, it's not quite that fast because there's quite a bit of resistance. Turn, 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 turn. Okay, I'm starting to see the wheel seem like it's inflating a little more just because there's not pressure on. Turn, turn, turn. You're watching that wheel, watching that wheel, watching that. I think it's starting to come up. Turn, 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 turn. The car's starting to shift. This is bad. Turn, turn. I should have stabilized. Hey, throw a brick under the wheel. Turn, turn. Oh, I've got about a half an inch of clearance. Now, Let me leave it jacked up, and let me take the wheel off and put the spare on, and then find out the spare doesn't have air in it either. Yeah. Yeah, make sure the spare has air in it, right? The spare tire in your vehicle does you no good if it's not inflated. And I just thought about it. The two vehicles I used to have, I no longer have. I knew their spare tires were inflated. I don't think my spare tires are inflated. I should probably do that. Anyway, because Murphy's Law says that now that I talked about it, it's going to happen to me. So I better inflate the spare tire. But anyway, turn, because the pitch is so small. But it's able to multiply your force considerably. Well, as far as the AMA, just continue to remember its output force, which again, assuming it's like a screw jack, you're lifting the weight of the vehicle or the object over the input force. That's the force you're applying. So I mean, this AMA is still weight over applied force or output force over input force. It's just the IMA we kind of want to redefine here for the screw jack. Questions on the screw? Let's look at the example problem here. We will do math with the screw. And look at the example problem 11.6 and read that if you would, Audrey.
A screw jack has a 24-inch handle and a pitch of 0.2 inches. The jack is rated at 25 tons. A force of 150 pounds on the handle is required to lift the full rated load. What are A, the IMA, and B, the AMA of the jack?
All right, so someone has determined for this particular jack, the most it can lift is 25 tons. And if you're going to get 25 tons out of this particular screw jack, you have to be able to push with a force of 150 pounds on that handle. If you push with that force, you'll get the full rated load. Something over 2,500 pounds, this jack just can't lift anyway. The structure of it is not strong enough to support that much weight. That's a pretty good jack, 25 tons. So we say it takes 150 pounds, that would be input force, right? To lift an output force of 25 tons. Thoughts on the AMA? Anyone see a problem with those numbers? Tons and pounds don't cancel. They have to cancel. How many pounds in a ton? 2,000. So 25 tons would be 50,000 pounds. Now the pounds can cancel. For that matter, I can cancel these zeros off as well. What is the AMA, the actual mechanical advantage of the screw? Or screw jack, I should say. 333.3, repeating, rounded off. It's at 2 sig figs, I think. Yeah, so we'll just say 330. Approximately 330 is the AMA. That means it can multiply your force by about 330 times what you put in. So Michael's a big, strong guy. He can put in the 150 pounds of force if he needs to. Audrey's not quite as big. Kendall's even smaller. Kendall might be like, well, I can't put in that much force. I can push with like 50 pounds. You're multiplied by 330. That's going to, what is that? 50 times 330. I mean, you're still going to get over 16,000 pounds of force out of it. You don't need 16,000 pounds. What if you had your typical car weighs maybe about 3,000 pounds? Well, let's say it's 3,300 pounds to make the numbers work. Well, all you need is 10 pounds of force on the handle. Makes it very easy to lift your car, not like Mr. Incredible style, but just using the screw jack. So there's the AMA. Then it asks for the IMA of the screw jack as well. In fact, it asks for the IMA first. We did the AMA out of order. All right, so for the IMA, we're going to take 2 times pi times the length of the handle. How long is the handle? 24 inches. Interesting. What about the pitch?
0.2.
So a fifth of it, that's a pretty wide pitch. A fifth of an inch? I feel like that's kind of wide for a screw jack, but whatever. 0.20 inches. That works then, so the inches do cancel. I was kind of like, inches, are we going to have to change that to 2 feet? No, because they gave you inches for the pitch as well. So those cancel, and so we multiply. 2 times pi times 24. And divide out the 0.2. Ooh, what's the IMA? 753.98, blah, blah, blah. We're still running off to 2 sig figs, so we'll say. So in an ideal world, based on the way this jack is designed, you should be able to multiply your force by 750 times. Meaning you put in 10 pounds, it'll lift 7,500. Why such a big discrepancy between IMA and AMA? What would cause there to be a big gap between those two numbers? Friction, right? So, thoughts? But if you want your jack to work better, should you maybe lubricate the jack or try to get rid of the friction? Or should you? Picture a frictionless screw jack for a minute. Picture it. You're turning the handle with very little problem, and it goes up, 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 up. And then you take your hand off the handle. If there were no friction, what happens to the handle? Okay? So you actually want the friction. Friction is your friend because it's friction allows you, in the case of your car jack, my car jack, to then pull the handle we were using out and use that as to get the lug nuts off, right? If there were no friction, it would just spin back out the other way. So we want friction. Yes, the IMA looks really, really good. That's plenty of AMA, right? I need the friction to help me out here a little bit and keep the handle from spinning back at me and hitting me and making me cry. And I'm already crying because of the spare tire that didn't have air in it, all that kind of thing. All right, questions on the screw. Feel like we understand screw. All right, next simple machine. Actually, it's pizza day. We will have to save next simple machine for another day. All right, stopping there for homework this evening. Read pages 168 to 170. So we'll read about the simple machines. That's fine. That's actually as far as you read anyway, so you haven't read about the next one. That worked out well. Read pages 168 to 170. On page 171, just 3 questions. Questions 19, 20, and 23. Page 71, 3 questions, 19, 20, and 23. And I want you to work one problem involving the screw, problem 11. So questions 19, 20, and 23, and then problem 11. Also make a note, your test will be Wednesday over chapters 10 through 12. That's lesson 80. So coming up in lesson 80, we'll have our test over chapters 10 and 11. All right, have a wonderful rest of your day, and you are dismissed.